Hi guys, Michelle Glass here, and we are continuing with our Chapter 2 lecture series, and our topic for this presentation is water. Okay, so let us look at some of the important properties of water. We've already talked before about water being reactive. We talked about both dehydration synthesis and hydrolysis reactions. Remember, we will be talking about these more in the future, but we looked in the dehydration synthesis reactions about pulling out a water molecule in order to make something new. And then in the hydrolysis reactions, we looked at the opposite. So we talked about splitting a water molecule in order to break down like that AB molecule into an AH and a BOH. So remember, we've already looked at that. Okay, we also see that water will be important in modulating the temperature. This is important in our bodies, but it's also important on our planet. So water has what's described as a high heat capacity. And so what that means is it takes a lot of energy to actually convert water from one state to another. So in order to make ice liquid, or in order to make liquid water steam, it's going to take a lot of heat in order to break those hydrogen bonds between the water molecules. And so it's absorbing a lot of energy as it's making those changes. So again, in our bodies, we can take advantage of that with evaporative cooling. So when our sweat is leaving our body as a gas, then a lot of that energy is going with it. So that's what's cooling our bodies down. This is important too on our planet. So coastal regions and regions close to large bodies of water, that water will absorb a lot of that energy so that those areas are not too hot, and also release some of that energy so those areas are not quite as cold. Okay, then we have this property of water that is described as water molecules as being both adhesive and cohesive. And all of this is tying into water's polarity and those hydrogen bonds that are going to be forming. Adhesive property is talking about water sticking to the sides of its containers, and the cohesive property is talking about water molecules sticking to each other. Now, you might have observed this before if you've ever had a glass of water that you filled up kind of overflowing, but it's not actually overflowing. You get that little bubble. That's because those water molecules are sticking to each other and then also to the sides of the glass, but you can obviously disrupt that if you keep adding water to that glass. If you've ever watched those little bugs called water striders, and they look like they're walking on top of the water, they're actually walking on those hydrogen bonds, so that's pretty cool. And this adhesive property is really important in terms of getting, actually both properties are important in terms of getting water from the roots of plants all the way to the tippy top of those leaves. So think about those really big trees that you have maybe in your neighborhood or in the woods, or like the Sequoia National Forest. Those really large trees are actually pulling water up through the vessels in the plant, and a big part of that kind of pull is coming from both the adhesive and cohesive properties of water. Okay, another important property for water that is making life on this planet as we know it is that ice is less dense than liquid. So remember, your water is polar, you have slight charges, and opposite charges attract, meaning like charges repel. So as that water is forming into the solid ice, then you're kind of making those water molecules kind of stuck in position. And so as they stick in position, they expand in order to get as much distance between opposite charge, as much distance as possible between like charges. And you guys know this, you've stuck that bottle of water in the freezer before, and then, you've seen that the plastic deforms, or, you can even burst open a container because of that expansion of ice. Now, this is important for aquatic life because this means that our ice is floating. So rather than our lakes and our oceans freezing from the bottom up and then pushing all life out of that system, we have our ice forming at the top and floating up to the top of those aquatic environments. And then our final property that we need to talk about is that water is a universal solvent. So we have some specific terms here that we need to make sure we understand. Okay, so the first term is the word solvent. Solvent is the dissolver in a solution. And so when we talk about water as the universal solvent, we're talking about water as being this universal dissolver. And what that means is more things, more molecules, more compounds are going to dissolve in water than in anything else. The solute is the term that's referring to the stuff that's actually dissolving in that water. And then once you have a solute dissolved in a solvent, we call that a solution. So let's make one right here. I have some regular salt, and I have my cup, and I have my thermos of water. Okay, so I am going to shake some salt into my cup. So this is going to be my solute, and I'm just putting a little bit in there. Get it away from my computer. And then I'm going to take my thermos of water, and I'm going to mix that in. You could do this with Kool-Aid, right? So you do that all the time, or you did as a kid maybe. You do it now maybe for your kids. Adding that Kool-Aid powder in with the water. Is making a salt solution in this case, or a Kool-Aid solution. So remember, the solute is the stuff, the particles, in this case the salt, that we are dissolving with our solvent, which is our water. Okay, and then the solution is both combined together. Let's take a look at why water is that universal solvent. So we're going to actually diagram that out. It all ties back to the idea that water is polar and has those slight charges, and also we know that opposite charges attract. And so what we're looking at with water as a universal solvent are these interactions between charges. So things that are polar will dissolve in water. Things that are ionic and they have a charge will dissolve well in water. So when we are talking about solubility and we're talking about water as a universal solvent, that doesn't mean that it can dissolve every single thing. What we see with solubility is that likes dissolve likes. And so polar things dissolve in polar things. Water's polar, so lots of polar things are going to be dissolving here. And then things that are not polar will not dissolve in water. Nonpolar dissolves in nonpolar. Polar dissolves in polar. Likes dissolve likes. So here we go. We're going to draw this out. So we're going to use our solute, which is our sodium chloride compound, ionic compound that we've already talked about previously. And then we're going to use our polar water molecule, which is our solvent. And what we will see is that the water molecules are going to position themselves such that the negatively charged oxygen molecules are going to be closest, the negatively charged oxygen atoms of the water molecule will be closest to those positively charged sodium ions, and then the positively charged hydrogen atoms of the water molecule will be closest to that negative chloride ion. And I didn't draw in my charges for my water molecule. I probably should have. Remember, again, the oxygen has a negative a -2 slight charge, and the hydrogen has a -1 slight charge. Now, because this is a water-based solution, we do describe this as an aqueous solution. And this is the reason that sodium chloride dissolves well in water. And so this is, again, likes dissolve likes. So water is a universal solvent because it's going to dissolve anything that is either partially charged, polar molecule, or fully charged, ionic compound. Molecules that do well with water, that like water, can be described as hydrophilic, where philos means water-loving. And then your hydrophobic molecules are those that are phobic of water, phobia, having a fear of water. And so we'll see again that nonpolar molecules such as fats are nonpolars, they're hydrophobic, they don't dissolve in water. And you already know that. You already know that oil and water don't mix, but this is the chemistry of why oil and water don't mix.